Here we go. So here's our first lesson on chemistry, and I just want to begin with introduction, okay? So we're not really going to do a whole lot today. It's kind of working our way in. I want to begin by talking about, well, what is chemistry? And I've got a definition on here for you. Chemistry is the study of change. But I want to be more specific than that. I designed my notes on purpose because what I'd like you guys to do is to write what we talk about, okay? So like, I often suggest to kids, bring highlighters. Don't write what's on the board here. It's already here, right? Write down, like, in this little section here, the stuff we talk about. Because I wanted to add to this. Chemistry is the study about the changes of matter. Chemistry is about how matter changes. I want to have more of a conversation. I'm not here to like read right off the board. I want to discuss this with you guys. Okay? What is matter? Does anybody know what matter is? Is fire matter? No. You want to take another stab at it? Close, you're halfway there. Ah, there's both of them. Yeah, you're close. Matter is not quite everything. I mean, for example, empty space, a vacuum. You guys ever heard of a vacuum? Not like a vacuum cleaner, but like a vacuum. It's literally like where anyone ever vacuum seal something to like put it in the freezer and you suck the air out of it? Right? Say you have a jar and you suck all the air out of the jar. There is no matter inside. It takes up space, but I don't know. I don't know whether that falls under everything, right? We need to be a bit more specific. So the two key components of matter is it has to have a mass and it has to take up space. Okay? A vacuum takes up space, but there's no mass there. Does that make sense? Fire is the example I gave earlier. Fire is actually a form of energy. Okay? Energy is not matter. They're actually different from each other. Actually, when we get to physics, energy is what we do to matter. So when we talk about physics, we're going to talk about how energy and matter are related to each other so that stuff does stuff. You know? Like, why does this pencil get thrown through the air? Why did that football tackler happen, right? Like, that's energy related. But chemistry is all about how matter changes. Maybe the best word, if I could break it down, maybe not everything. I like this one, though. Matter is our stuff. But there is some stuff that's not matter. So does that make sense? This is what chemistry is about. It's about how things change, the tangible things that we can see and feel in our world around us change, like metal rusting, hydrocarbons combusting, heck, even just making wine. That's change, right? And this is a good visual right here. Molecules have to change from one to another. Here I have nitrogen. If you guys don't know this from last year in grade 9, N is for nitrogen. This is a nitrogen molecule. This is oxygen molecules. And it looks like they are combining in a reaction to make a molecule called nitrogen dioxide. Right? Now, that's a chemical change. This used to look like this. Now it looks like this. One of the analogies I love to give is my daughters. I use them all the time in my class. Maybe you can consider matter to be kind of like Lego blocks. My daughters like to play with Lego. We have all these like little princess Lego pieces. They love them, right? Right? Well, originally she might have a castle made, right? But then she takes the molecules for the castle and she rearranges them and makes them into a car. Does that make sense? And that's kind of what chemistry is. We want to talk about how our stuff changes because we don't live in a static world. We live in a world where our things are going to manipulate from one form to another. I mean, right off the bat, your body has to do this on a regular basis, right? We need to breathe in oxygen and breathe out carbon dioxide, right? And if our body did not undergo a change like that, we would die because we need that oxygen to get converted and for us to do cellular respiration and that stuff. You know what I'm saying here? So that's what we're going to talk about. On this slide right here, I have some of the things that chemists were going to want to do. Chemists and scientists, we need to observe things. There's always a before and an afterwards, right? Before it looked like this, after it looked like this. And you guys might have seen this before, right? Sometimes we write a chemical equation where this stuff plus this stuff turns into this stuff. There's a before and there's an after. And so scientists are all about change. Chemists especially, right? Chemists care about change. So let me give you some examples of changes we might be looking for. Different phases of matter, right? For example, it's a change when all of a sudden it goes from being a solid block of ice to liquid. That was actually a physical change, by the way, not a chemical change, but it's still a change, right? Maybe a gas is produced. Does anybody know this word precipitate in terms of chemistry? Yeah. Anybody know what a precipitate is? Yeah, take it. Perfect. It's actually this exact picture right here. Yeah. When you have like some sort of cloudy solid that forms in a liquid, it's a precipitate. Okay. And so sometimes when we mix chemicals together, you get some cloudiness forming. I would not want to see a precipitate in my hot tub. That would be gross. Does that make sense? It would be an example of chemical change, and I probably should turn the filter on and clean it and add chlorine and that stuff, right? New smells and odors are a good example of chemical change. Color changes, and this is a really big one, anything that releases or absorbs energy. These are all examples of change. Now, we can actually break these changes, though, down into two categories. So more words I need you to know. Qualitative and quantitative. And I have a feeling that you may know what quantitative means if you know what the word quantity means. What's a quantity? A number, yeah. A quantitative observation has a number associated with it. N-U-M-B-E-R. For example, I could tell you that it used to weigh 10 grams, and now it weighs 9 grams. That's a quantitative amount. Right? I could tell you that the pH of my hot tub used to be 7.5, and now it's 8.2. I put a number to it. Does that make sense? Qualitative describes qualities, and so I could say that it once was red and now it's yellow. Can I put a number to that? Actually, if you know how to do wavelengths, you could, I guess. But for our purposes, I guess no. You know what I'm saying here? I could ask you, was it a solid or a liquid? And that's really a quality, not a quantity. I don't have a number associated with it. So basically, this has numbers, and this has like descriptions, I guess. Descriptions. And so one of the things that we're going to do in our labs, and I want to do a lot of activities in labs, is I'm going to ask you to describe what you see in terms of anything that you can number and anything that I guess you just have to describe in other words. Right? Really not, one of these isn't better than the other, but I will say this. Whenever we do quantitative observations, that usually involves us doing some sort of math. And a lot of science involves math. So let's talk a bit about those properties then. Okay. There are actually two different types of properties. You guys should know this from grade 9, I'm hoping. So I hope this isn't like brand new, but they're considered to be physical versus chemical changes. Okay. A great example of a physical property would be its boiling point. What's the boiling point of water? That's a quantitative observation. We know that the number happens to be there, right? That's a quantity, right? But that's a physical change. And the reason why is that water didn't physically change what it was. It went from being water liquid to being water vapor. Does that make sense? It didn't go from being water liquid to being hydrogen or to being sulfur. Does that make sense? Like, if it changes what it is, that's a chemical change. But if it's the same thing and it changes its state of matter, that's a physical property. And so these things are usually the same. Like, for example, look at this bromine right here. You guys see how there's like some liquid sitting in the bottom right here? But there's also some stuff up here that's evaporated into gas. Its color's the same though, right? Isn't it? I mean, I know it's a bit deeper color right here because it's more concentrated, but it's got like this reddy brown color right here. It's still reddy brown right here. That's because when it evaporates, that's a physical change. It's still bromine. Does that make sense? But if, and this wouldn't happen, but if bromine turned into chlorine, well, it would now have a color change because it's got a change in color because of the fact that it's now undergone a chemical property, a chemical change. So I hope you guys kind of know these words here. Physical describes the physical appearance, but a chemical property means that you have to react it. This is the part of the word I want to work on right here. If it's a chemical property, it reacts. It occurs like with something else. Something is done to change what it is. Let me give you another example for my daughter here. Imagine that Kinsey is playing with a Lego blocks, and she has all her Lego blocks out. She changes her car into a house. But like, she still is using Lego blocks. Does that make sense? Maybe that's a physical change, because it's really not different in any way. But let's say that somehow this doesn't make sense, but like, let's say that somehow her Lego blocks get melted. And all of a sudden, they don't have the little Lego nubs on the top anymore, and they're all melted together, and they turn into marbles. Now she wants to play a different game. Can you see how that's now a chemical change? Because like what she was working with is now chemically different. I wanted to use the word physically different, but like it's probably not the right word to use. It's now different stuff. So when we burn things, when we react them with water, when we add them to heat, they have changed. And there's one more thing about these things right here, is that usually these things are not reversible. Let me give you a couple of examples here. Let's say that I light something on fire. Chemical or physical changes and properties we're talking about if I light it on fire. Yeah, because it's now something different. Literally, the piece of paper that say I burned has now turned into carbon dioxide, and it has now escaped, and it's gone. I'm not getting it back, right? But let's say I take that same piece of paper and I rip it in half. That's a physical change. Does that make sense? So similar things with physical properties. Okay? So if we're going to talk then about matter and what it's made of, there's a categorization system, a classification, a lot of vocabulary you guys need to know. And I bet you know this terminology as well, so I'm sorry if I'm kind of boring you today, but you probably heard this term before. We're going to start with atoms. Okay? And atoms and molecules, they make up matter. And I think the best way of describing an atom would be if you had, like, say, just, what's a good example? Oxygen. If you just had O for oxygen, that would be an oxygen atom. Or N, a nitrogen atom. Or H, a hydrogen atom. But a molecule would be if you had like H attached to an O attached to an H. What do we call that? Yeah, it's water, right? And so sometimes they can be by themselves, but most of the time they're not by themselves. Sometimes they're in a group. And in a group like this, we call them molecules. And really, these things make up everything that's going to sit here. And I actually already have that terminology sitting here. We actually give a better name to it. We call those things elements and compounds. An element, you guys see the periodic table that's behind here, over behind Rye? Yeah. Rye and, what's your name again? Gabby, Rye and Gabby. Periodic table over here, right? There are like 117-ish, depends on the synthetic ones, known elements, right? And often they're by themselves. Like I could have pure gold. I could have lead. But often they're in groupings, in compounds. Okay? Now, sometimes that's just not enough on its own. Sometimes we have mixtures. And these mixtures fall into one of two categories. Either they look the same throughout, or they look different. And the prefixes we use are homogeneous and heterogeneous. Okay? And I've got some examples on the next slide here that I'm going to use to kind of illustrate it. Do you guys know this vocabulary, though? You've seen it before at some point, maybe? Okay, I'm going to go a little quicker then. Like an element, you can't break it down. It is as small as it gets, other than subatomic particles, which we'll get to. Technically, there's protons, neutrons, and electrons, but we're going to call those the basic building blocks, the elements up there. Compounds there are when you put them together, like CO2, H2O. And you can kind of see that this guy right here, this picture here would be an element, because it's just the one thing. This one right here is also an element, actually, because even though they're in groups of two, they're actually just still yellow. For example, this could be O2, oxygen gas. They actually come in groups of two, but it's still just oxygen. This could be, I don't know, carbon. So these guys would be elements. The compound then, how do I change my color here? The compound would be this guy right here. Can you guys see how there's two different colors in there? Right, put together? That makes that a compound. Okay. This thing right here is what's not on our page. This would be a mixture. And really, almost all the stuff we see in the world is some sort of mixture. Right? I mean, unless it's pure, and that's where the word comes from. A pure substance is just one thing. A mixture is where you've got like a collection of things. Like, for example, I'm going to go to this slide here. I hop around in slides, by the way, sometimes, so I'm sorry if that throws you off. Find this picture here. It's 2 slides in. Here's a good example of some mixtures. Pudding is a mixture. But like, there's multiple things inside pudding. I know that because I made the pudding. I put in the chocolate powder and the milk, right? So clearly there's at least 2 different things inside the pudding. But if it looks the same all the way throughout, we call it a homogeneous mixture, meaning the same, right? Whereas if I go and get some of the trail mix, it's also a mixture, but what's different about it? I can see the differences. I can literally go, hey, there's an M&M. My wife is notorious when we buy the mix there for eating all the M&Ms out of it, and then I get the rest that's left over, and there's no chocolate left. And it's like, anyways, does that make sense? So if you can literally see what's inside there, it's a heterogeneous mixture. All right. Whereas if I go back a slide here, Pure substances, then, are where there's just one thing. This right here cannot be a pure substance. This candy conglomeration is clearly a mixture because there's a whole bunch of different pieces inside there. Does that make sense? So 4 terms: element, compound, heterogeneous mixture, homogeneous mixture. Okay? And this kind of is a classification scheme that you can use as well. It's either pure or it's a mixture. And technically the heterogeneous mixtures, there's actually a couple different types. I'm not going to talk about them right now because it's actually one of the things I'm going to ask you to look up later. The difference between suspensions, colloids, and mechanical mixtures. But I need you guys to know that these are things, though, where you can actually see the differences. A solution is where you can't see the difference. Okay, we're back to talking about properties again here. I've already discussed this concept, so I'll just kind of rehash it again here. We try to identify pure substances by their properties. Why does it have to be a pure substance that I'm trying to use properties to figure out? Why can't I use a mixture? Because a mixture would have lots of properties, right? If I were to ask you what the melting point is of this, what's the melting point of this? Well, it depends on what I'm talking about. The cashew might melt at a different temperature than the chocolate. I'm pretty sure the chocolate's melting first, right? I mean, as long as the coating on the outside doesn't stay there, maybe not, right? Does that make sense? So like different things together in a mixture, they're going to have different properties. This guy's got a property of red. This one's got a property of brown. Does that make sense? So when we're talking about properties, we're really trying to use those mostly on pure substances because we got to be talking about just one type of thing, right? It has to be, here's the key word, consistent, right? And this is what we discussed already. A physical property does not change the identity. So let's say I rip something in half. It's still the same thing. There's just 2 of them, right? Let's say that I burn it, though. Yeah, it's going to ruin my sample, and it's going to undergo a chemical change. Fair enough? Really, the key for most scenarios, can you reverse it? If you could undo it, it's probably a physical change, a physical property you're talking about. Okay, this next section here is kind of like a bit of a divide. We're now going to talk a little bit about some of the safety behind chemicals. It's one of the mandatory things we have to do. So I'm sorry if this is kind of the boring section here. We're going to talk about safety hazard symbols that you might see on chemicals. You guys have seen these before? I'm pretty sure it's in like grade 8 and 9 curriculum too, right? Flammable, toxic. So these are safety hazard symbols. Here's what I need you guys to know. This is literally a question on your assignment. On your assignment. If I give you a safety hazard symbol, do you guys know that like the yellow triangle means caution, the orange diamond means warning, and the red octagon is the most dangerous, it means danger? Okay. Actually, a student helped me come up with a really clever way of remembering the order they went in. I never thought of this before. A triangle has 3 sides to it. 3 is a small number. A diamond has 4 sides to it. 4 is bigger than 3. Octagon has 8 sides to it. I probably can't draw a very good octagon here. 8 has the most number of sides to it. I thought that was brilliant, actually. So if you're trying to remember which order they go in, triangle, diamond, octagon, based on how many sides they have. So. And then, I don't know if this helps at all, but like I use the colors of like stop signs and red lights and stuff. Like yellow is kind of like maybe I should stop, and red means you should stop for the red light. And I just have to remember that orange is in between, I guess. So because there's no green for go. Anyways, inside there's the symbols, and you guys have probably seen these symbols before, right? You've got the flammable, the toxic, the explosive, and I need you guys to know these symbols, which kind of sucks because you just got to memorize them. But I got to be honest, most of them are like intuitive. Like you look at the picture and you kind of know what's happening, right? Like I don't even think I need to know English to look at this picture here and go, that's exploding, or to look at this picture right here and go, that's bones, it's eating away my skin, right? Like, so most of these pictures are intuitive. They used to look like this. So here's our next slide. These were the 8 symbols. They changed in 2015. I don't know that any of you guys knew this, but they changed in 2015. And most businesses and places that matter, schools included, they didn't have to officially change until like 2018, 2019. So this is actually what the old symbols are. Anybody ever seen like these ones before? Okay. The new ones are what I have to test you on, or what I'm going to test you on, because they're the current ones. There used to be 8, now there are 10. That's the only difference, okay? So really the first slide right here, this is the pre-2015 one. Here's the newest ones. But like, again, don't most of them kind of make sense? Like, this canister is compressed gas. That's what it was before. This is something that's flammable. Flammable and oxidizing are very similar. I can talk to you more later if you really care about the differences. Here's something exploding. Here's something poisonous, harmful, and fatal. Here's something, you guys have probably seen the biohazard material one before, right? This is something corrosive. This causes health hazards. This one's new, by the way. This is something harmful. This is harmful to the environment. Because, I mean, look, there's like, I think that's a fish, right? Is that a fish right in there? So, they're pretty intuitive. I just need to know, you guys know which ones are which, okay? Okay, here's another slide that has them on there as well. You guys can read them over if you'd like, but you have experience with this. Here's my last thing, then we can call it a day in a bit here. All scientific chemicals should come with what's known as a Material Safety Data Sheet, MSDS. But in 2015, they changed how they were categorizing things. I think the reason why they changed things is that in different places in the world, they had different names for them. In Canada, we called it an MSDS. In the United States, they called it an SDS. I think they just wanted it to be uniform everywhere. So from now on, it's actually known as an SDS. It's no longer a Material Safety Data Sheet. It's actually now known as a Safety Data Sheet. So you just got to get rid of the M, I guess, whatever. Anyways, these are like information sheets that you would get with dangerous chemicals. Like if any of you guys have a job and you're working with cleaners and stuff, you should hopefully have these nearby for you to read, because it'll tell you things like physical data, melting points, boiling points. Here's a really important one sometimes. What to do if it spills, right? Sometimes you pour sand on it and clean it up. Sometimes you got to call in the hazmat team and they got to wear the full plastic suits, right? So like, it's sort of the sort of stuff you should know, right? I printed off a basic one here. It's for this super dangerous chemical. You might have heard of it. It's called sodium chloride. This stuff is like, actually it tastes really good on fries. It's salt. You guys know that? Sodium chloride is salt. Yeah. But salt is a chemical, so it's got a safety data sheet. You guys might notice here that there's a little thing up in the corner here. It's got like some different colors in it. It's got a 1 for health, a 0 for fire, and a 0 for reactivity. It's actually a really safe compound. You guys ever really been worried about salt? Not really. I mean, it's not really going to light on fire. It would take quite a bit for it to light on fire. It's not really reactive. Like when you put salt on French fries, it doesn't explode, which is good. Because in other chemical scenarios, it can be reactive, right? Salt does not light on fire all that easily, right? It does have a 1 for health. Yeah, if you consumed a lot of salt, it could be dangerous to your body, right? I mean, most things, if you consume enough of it, it's going to cause a problem, right? No. So, I mean, it's going to give you high cholesterol, right? So, anyways, this is what it would look like. It has a whole bunch of sections to it, things like composition information on ingredients, phone numbers to call, hazards information. I mean, it goes beyond this. There's like probably 4 or 5 pages to it. It'll tell you what to do in case of a spill. On this one, I'm pretty sure it's going to say wipe up with paper towel. Right? But on other ones, for example, if I spill an acid, I would use a base to neutralize it, and it would tell me how to do that. Right? So anyways, that's the safety data sheet. And then here's the last thing. This is that little code in the corner here. It kind of tells you just a real brief overview of like what you should be worried about. So like how dangerous it is to your health is over here. How bad is it for fire? At what temperature might it possibly auto-ignite? There's a few properties of compounds where like it can actually spontaneously combust just due to ambient temperature in the air. And so we're worried about those sorts of things. Instability, like could it detonate? Salt's not blowing up on us, thank goodness, right? It's stable. So I think that was my last slide, right? Perfect. Cool. Okay, so that's my first lesson. It took me 23 minutes and 40-something seconds, so I'm going to stop the video now.